Oh, as Ninat said, that's the title. I'll be talking about climate of the Common Era. And actually, I should mention that I'm just standing here. The work has been done by a large consortium. Ninat mentioned we do coordination work. That is a prime example of how coordination went well and successful. So I'll explain a little bit about that as well. Okay, so we talk about climate of the Common Era. And this is the Common Era, year 1 to 2013. Used to be under Domini, but Common Era is now much better especially if you look at a global scale where non-Christian regions are also involved. So this is the Common Era, and this is its instrument-based temperature record. So depending on how brave you are, you can extend it into the mid-19th century, but that's all we have. So it's impressive from its amplitude, but not impressive from its reach. So if you look at the same data, just over this, over the whole spread over the whole range from the 19th century to today, we see this increase in temperature. I mean, you've all seen this a million times. But that's the global average. It's interesting if you want to do budgets, energy budgets and things like that. But if you look into more detail, as is done in this figure here, again, the time axis from 1880 to 2010. But now here, there's a latitudinal transact, if you want, from the north to the south, and the colors indicate the warmth at any particular latitudinal band. And there you see that, the global average is just an average. Actually, there's a lot of variability regionally or latitudinally in this case, like in the high northern latitudes, much more warming than there are zones where there's only moderate temperature change. The northern hemisphere, sees more temperature change than the southern hemisphere and things like that. And this point about looking at the regional scale is also emphasized if you look at a map here, spatial temperature variability from the last decade compared to 1950s to 80s to 80. There's a lot of heterogeneity on this map. There's even some coolings in places. So if someone finds cooling in one place, it doesn't mean that global warming isn't happening. And at the same time, if we know that the globe is warming, it doesn't mean that every place on the planet warms. So if you want to have a meaningful record, we should go into more detail. And it's great that I see Carrie Crumley here, because I have this slide from iHope. That's from the science plan of iHope, which used to be here rooted in Stockholm. So many of you might know about it. It was still is a very ambitious project, trying to combine the history of people with the history of environment, of climatic change, all the interactions, and I think iHope wants to understand the interactions systematically, not just in a deterministic way. So the idea is to collect all sorts of climatic data. I mean, I don't want you to understand the graph, but it kind of illustrates the complexity of the whole problem. And if you want to understand societal changes, then we need to have a much better environmental records to compare them with than what we currently use. There are a few examples how climate society interactions are often depicted. That's an almost classic example by now from Hauke et al., published in Science, of course, because it's an interesting subject. But so there's one record from Cariaco Basin of Venezuela, and it shows that there were possibly droughts and this is related to Maya collapses. A similar way of looking at Chinese dynasties was done here from lake sediments in southern China. So these are both lake records, and here in colors are the Chinese dynasties, and the point was made that the lake records show that there's this drought here and there, and that drought induces a change in dynasty, basically uprisings of people. Okay, again, a very simple comparison of climate and its impact on societies. And a final example, a recent climate record from Central Europe based on tree rings, a precipitation record and a temperature record again, where then people plot the history of Europe against a climate record and make inferences at a very simple level. I mean, it's very interesting. These things are published in high-profile journals, but we should be able to do better, certainly from the climate environment side, and that's what we want to do. That's why we established this Pages 2K network. It's a network of 9 groups. Working groups in Pages, and we coordinate them, we orchestrate them. Although actually we leave them a lot of freedom. You can see that somehow already. We have acronyms, yes, but they all many of them are very individual. So it does reflect the level of freedom that each individual group does have. And many people involved, and this is now just the author list of a recent paper, and that's an intermediate product, so the project is ongoing, so we're not finished, there's more to come, but there's most of what I'm showing is based on this paper. So this is an author list, and actually there are even more people somehow involved in workshops, and so this is kind of the core group. The objectives of this whole network would be to compile data, to quality control the data, to reconstruct regional climate, temperature, precipitation, maybe even pressure fields, compare the data with models, and then analyze climate in regions and globally. There are some scientific goals. Determine the main modes of climate variability on subdecadal to orbital, longer, 10,000 years timescales. Determine the relation between climate variability and climate forcing, which includes also the question how strong is the human component to climate change today, and evaluate the regional expression of global change. So how do we do this usually? Here we go. The regional groups compiled data. It was not much. It was not intended that people do field work and generate data. It was just intended that people could use the data that are already out there. So it's really adding value to the data that are produced already anyway. So anyway, it's a relatively cheap project for quite a good output, I think. So all the groups screened what they found were the best data in their region, and we relied on the regional expertise. What is best? Obviously, in Antarctica, ice cores make 100%. In South America, there's more variety. There's tree rings and instrumental data and ice cores and lake sediments and so on. Some groups found that tree rings only are the best source of information. Others made use of the variety of archives that are available. In total, in this paper, for all these regions, we used 511 records. Africa, that's also a result, has basically only one record, Lake Tanganyika here, that would be good enough as a temperature record. So more work to be done in Africa. if you want a temperature reconstruction for there. So how do we do this in general? How do we get temperatures from times long past? Okay, not very good. Anyway, that's a tree. Someone trying coring the trunk of the tree, and then getting a little sample, a long thin wood sample that show the tree rings. Probably you know that the tree rings grow thicker if conditions are favorable, and they're thinner if they are unfavorable. Ice core is another prominent example. So people go to Antarctica or to Greenland or to high altitude glaciers, drill ice. Get these ice cores again, long and thin samples. And if you're lucky, then you have annual layering that gives you very good time control. Or in the tropics, more popular are corals. Again, you have to drill corals. Get an elongated sample again, and oops, okay. One doesn't see that, but it doesn't matter. So again, often you have annual banding in the corals, so very good archive. And all these archives, they carry some signal that can be interpreted in terms of environmental change. For example, the corals, often they incorporate trace metals in a particular relationship with calcium, depending on the temperature. The tree rings, for the tree rings, it's the ring width or the wood density. For ice, it's the oxygen isotope signature of the ice. And here we have a lake. So you can go out onto the lake. That is Derek Kaufman. So I should mention him because he's one of the major drivers of this whole initiative. Yeah, you spend some time at the lake. You install a drilling facility, and then again you get these long samples. And this would be, if you cut them open, that would be the mud from the bottom of the lake. Again, you see the layering, and so if you're lucky, they are annual layers. And then you can measure something like some geochemical signal, or look at the composition of microfossils and figure out the temperature. Okay. Good. So these data have been put together by all these regional groups, and these are the results. These are seven temperature records, one for each region. Here's the time scale again, from 0 to 2,000 years. So we see several things. One is that not all regions succeeded in producing a reliable temperature reconstruction all the way back to 2,000 years. Again, so it was up to the individual groups to deliver what they think they can justify. We have 2,000 years from the Arctic, from Europe, and almost from Antarctica, but other regions stopped earlier than that. Again, the kind of archives that are used are very different. Also, actually, the statistical methods. So it was up to the groups to apply whatever statistics they thought would work best. That results in a relatively heterogeneous data set. And of course, yeah, sometimes you would like to have things comparable directly. So it can be considered the heterogeneity, could be considered a weakness. But on the other hand, if you find common signals in these heterogeneous records, you can't blame a systematic bias. So you can look at positively at the diversity of the approaches. Okay, let's get that. So, and you can compare the temperature reconstructions with the instrument-based temperatures and see how well the reconstructions based on the archives, how well they represent the entire region. So these little light blue bits of curve, they represent the average temperature in the region that represents the box of the region. Okay, so that is now a different view where hopefully one sees more clearly what is going on. These data are now standardized and binned into 30 years. And you have all the regions here, Arctic kind of oriented north-south roughly, Arctic, Europe, Asia, North America, Australasia, and South America, and Antarctica. So from 0 to 2000. Didn't go beyond 2000 because many of the data sets don't reach all the way to present. I mean, maybe they were sampled 10 years ago and so on. So, the color coding means obviously that the warm colors mean warm temperatures, the cold colors mean cold temperatures, and now if you squeeze your eyes a bit, or if you're short-sighted like I am, you just can remove your glasses and you see a pattern that seems to have warmer temperatures over here in the first millennium and colder temperatures in the second millennium of the Common Era. And we can also prove that in numbers. That's the first millennium minus the second millennium. And here we have negative numbers, so a cooling from here to there all the way, or through all regions where the record is long enough. You can also look at this trend by doing a least squares linear regression in all the regions. So everywhere there's a negative trend, except for North America, where we can't say very well, and all the trends are significant to mildly significant. Another thing you can do to check whether this long-term cooling trend over 2,000 years or so, whether it's significant or whether it's significant, you can look at the oceans, because so far the regional groups they're mostly continental based, but there's one group that specifically looks at ocean records. And here I want to do a little excursion on how they are organized. So I'm putting up the website here, because it's for me it's an example of how a future way of how working groups can operate. They use all the digital possibilities that at least we can offer. So they have a nice website where the goals and instructions and so on are well laid out. They made calls for participation through list servers, through newsletters, and so on. So they really involved the community. It started off with a data harvesting exercise from existing databases. And it's quite remarkable that so many people volunteered to do the work, to skim through databases and collect the relevant data and put them into a metadatabase. So about 75 people volunteered for that. Then a smaller group of 26 people volunteered to do the synthesis, to do really the data crunching and so on. And then we hear from the Pages office, and so we do some support and steering. So now I show results from this low resolution group. So they have a high resolution group from the ocean where they mostly look at coral data annually resolved. But we want to look at the 2,000 years, and there's no annually resolved 2,000-year record. So you have to rely on low resolution, which is sediment data. So this is the entire set of metadata that was collected from the oceans by this group, by these 75 plus people. After quality screening and check, for example, how many of those really reach back 2,000 years with high enough resolution, what remains is 44 records with a certain bias in the oceans. Nevertheless, 44 high quality, 2,000 year long ocean surface temperature reconstructions. And if you put them all together, you see a lot of wiggles. Actually, you don't see anything on these. This is now 6,000 years, so some go back even more than 2,000 years. These are the original temperatures. These are standardized so that they lie all on top of each other. So what they did then was to bin the records of the last 2,000 years into 200-year chunks. And then the picture becomes a bit more clear. So these are the bin records, so in 200-year steps. And these are the same data, the 44 records, in box and whiskers plots. And suddenly you find that you find the same cooling trend over 2,000 years, except for the last 200 years. There's a lot of variability, and it's almost obvious where this comes from. So that seems to be a robust feature, cooling over 2,000 years. Why is that? It's maybe not too surprising in the northern hemisphere, because the geometry of the Earth relative to the Sun results in a decrease in energy from the Sun in the northern hemisphere in summer. So, because most of these reconstructions are dominated by summer temperatures, and most of the energy is received during summer, you would actually expect such a cooling. And yet that's what you see in the northern hemisphere. It's a little bit more puzzling that also in the southern hemisphere you find this long-term cooling, because here actually in summer in the southern hemisphere the trend of the energy from the sun is increasing. So it's a bit of an enigma. But there is an explanation that goes that basically the ocean around, that is strongly represented in the southern hemisphere, delays the response of temperature to insolation. And during October in the southern hemisphere, the insolation actually decreases. So with a 2-month delay in temperature response, we can explain the consistent cooling also in the southern hemisphere over several millennia. Good. That would be conclusions about this long-term trend. So most, if not all, regions and the ocean cooled over the duration of the record before the 20th century. And the cooling trend was actually then reversed in all regions except Antarctica. Anyway, I should have stressed that. Yeah, I mean, you see the red colors here at the very end of the record. So after 1900, suddenly the cooling is reversed. All regions except here, Antarctica, are warming. So, and the reason for this cooling is probably orbitally induced changes in insolation. Sorry for the X. If I extend the conclusions to some implications, then I find 2 points. One is, if the warming back in time is continuous, then regions must have been warmer than today at some point. So the point being that, I mean, we are in a constant discussion with climate. Well, people questioning whether current climate warming is significant. And one claim is that if sometime in the past climate was warmer than today, then there's nothing special about today's warming. Although that is, I mean, it's a false argument. And the point here is that at some point in the past, of course, it was warmer. With the trend we observe, and we can clearly predict that, and it's completely fine. And it has a reason of probably of orbitally induced solar insolation decrease. Another implication is the cooling trend makes the recent warming an even more remarkable feature. So we have that cooling and suddenly it stops. So why is that? Well, I think we have an idea. Okay, so another observation is about of these data, or we can retrieve from the data, is about the so-called medieval climate anomaly and the Little Ice Age. Maybe a concept that is familiar, especially if you look at societies and history. We had a whole pages newsletter about the medieval climate anomaly, trying to figure out the pattern globally. Underlying here in this title picture is a very old temperature record. So that's a warm phase around 1100, 1300 in Europe, and a cool phase that follows, which is then termed the little ice age. Here I have the big picture. These concepts come from Europe, North America, and often used globally. With our records now, we can check whether they really can be used globally. The answer is no. Certainly not for the medieval climate anomaly, where we would look for a consistent warming globally, but regions are very heterogeneous in that respect. So in the northern hemisphere, there's an early warmish phase around 830 to 1100, whereas in the southern hemisphere, in Australasia and South America, there's a warm phase clearly much later than in the northern hemisphere. And on Antarctica, again, Antarctica does a whole different thing. There's no such warm phase at all. You can draw a box here in the over the 17th to the 19th century of a generally cool period. But if we try to fix boundaries to a little ice age, let's say with the blue colors, we tried that, but there's no clear answer. So again, the temperature history between regions is so ununiform. What is it? Heterogeneous, that we cannot identify a little ice age cooling either. That's an attempt to explain these temperature anomalies over the over centuries. The cool temperatures here and the warmer-ish temperatures there. Simply that the cool temperatures over the last few centuries had probably to do with higher volcanic activity and some solar lows. So together, they shifted the energy balance that way that many regions globally did cool, but not to the extent as we see today. And that's what we should look at next. The first time conclusions about the century scale anomalies. There's no globally warm or cold intervals that define a worldwide medieval climate anomaly or little ice age. And the implications are that the variability between regions and between hemispheres can be substantial and occur superimposed on longer term trends. So finally, So how can we assess the last century and last decade's temperature record in the context of the longer term past? If you compare the last century here, this thin box, with the previous coldish centuries, then we find that the last century was way warmer in all regions except for Antarctica. So it was warmer by 1/3 of a degree to more than 1 degree. So that's what I mentioned earlier as this reversal of the cooling trend. It's quite remarkable. If you look at only the previous 30-year periods, 1970 to 2000, there are several regions where within their records there was no warmer 30-year period. And in the Arctic, in Asia, in Australasia. There are some regions where there was actually a warmer 30-year period sometime in the record. So it's the data show that sometimes the current warming seems to be not unprecedented in the historical record. And we can also look at that if we now dare to produce a global average of all these regional curves, a global average, then with again some box and whiskers plot with uncertainties, then that is the record. And again, you can decide whether 2000. The last decade, the last 30-year period was the warmest or not. It's actually relatively irrelevant. It's more symbolic. But if you really want, if you're after record temperatures, we could just add the last decade. Oh, hold on. Right. Because that's what happened over the last decade. So there was warming of several tens of degrees, and with that average temperature between 2001 and 2011, we're definitely above the global temperature over the last 2,000 years. So, conclusion. These 30 years were the warmest 30-year period. Some regions experienced 30-year periods that were warmer. But the implications are that the warming over the last few decades was substantial, but not unprecedented in several of the regions. However, the coherency of warming across all the regions except Antarctica, that is unique. Now you should emphasize really that point. There's no 30-year period where almost all regions warmed synchronously. So that is unprecedented. Okay, so then the conclusions in overview again. Most, if not all, regions and the ocean cooled over the duration of the record before the 20th century. This long-term cooling trend. Cooling trend was reversed in all regions except Antarctica. So Antarctica is doing its own thing. It's shielded by a large ocean. But orbitally induced changes in insulation are the likely driver. So we can explain this cooling. And I think we can also explain the warming in the 20th century. No globally synchronous warm or cold intervals that define a worldwide medieval climate anomaly or little ice age were detected. And the last 30 years were the warmest 30-year periods, while some regions experienced 30-year periods that were warmer. So that's as far as we got for now. It's an ongoing project, as I said. And the next steps will be that we abandon these regional average temperature records and really going into the spatial sphere. That we can really basically have maps of temperature change evolving through time. And that is then something that can be really even better be used for comparison with how societies respond. What we also plan to do, because actually temperature is nice to have, but it's not so societally and ecologically relevant in many places. What we want is precipitation. It's a bit harder because the spatial heterogeneity is larger, but that's also nevertheless one of the next steps. So stay tuned, and I think that's all I have. Yes, thank you.